the flow coming and joining into the stream at different places, the form of lateral, but at that particular section, that is input, remember. So that means in the process of applying this equation in any method, you have to consider the one-dimensional flow form. That is one thing. And the second is, as per the Chassis principles and the Manning's proposed concept, hydrostatic pressures prevails always, and the hydrostatic pressures we always consider ignore these vertical accelerations. Vertical accelerations, we are ignoring them. Please remember that. And streamline, the curvature is small. That is one thing. So we are taking the reaches almost straight. So because river reaches having many bends, river bends are there. So when you are applying these methods, you have to be very careful about the river bends. So you cannot, this is what the mistake many river engineers are doing. They are simply taking a river reach length is 100 kilometers at a long stretch. That is not correct to my sense. The reason is that a river is having many bends inside, but inside the considered reach. So that causes certain impact in the river flows. So when you are calculating, applying such models, this kind of mathematical models, you have to be very careful about this phenomena, river bends, etc., river curvature, etc. So as far as possible, you try to take the shorter spans of the reaches that governs the flow, a nonlinear curvature of the river into a linear curvature of the rivers. Remember that. The bottom slopes of the channel usually small. That is one constraint. Assumptions here. So that is one thing. So I will talk much on the small slope and high slopes at the later phase. Okay, and the Manning's equation is to be used. That means that you are considering the surface roughness variations, vertical roughness variations, and the longitudinal roughness variation also can be considered in this particular equation, and the fluid is incompressible. So these are the assumptions that we usually adopt in these particular mathematical models. So here I'm what do you say, that the various combinations, various floods. I'm giving a comprehensive summary here. So momentum equations, based on the momentum equation components, I can classify these things. Of course, this Professor Subankar Karmakar from IIT Bombay has defined like this. Of course, many people are defining like this in his NPTEL lecture. I've taken from it. But whatever was told is everybody is saying the same. So SF is S0 is a kinematic wave, steady uniform flow you expect there. And SF is S0 means del Y by del X is the flow depth variation, water level variation in the longitudinal direction. Pressure variation in the longitudinal direction is causing the non-inertial form that is called diffusion and diffusive wave. And the S0 and the local convective acceleration, if you only consider ignoring the local acceleration, then you can say it is steady non-uniform. And if you take all terms, we say it is unsteady non-uniform flow or a dynamic wave. These are the main flood waves, and the based on the momentum equation were derived from this invariance equation. As I told you, the gravity wave, it is only the flow of the waves that are occurring on the top layers of the streams at a particular height due to slopes. For a zero slope and a considerable slope, if you take, these waves occur due to gravity forces that are prevailing in the particular river reach. This is the gravity. So you can now use this invariant equation, convert into some other form also. Here I'm highlighting the dynamic wave into the conservation form. I'm replacing the del Y by del X with the Y. The flow depth is replaced with the charge. So Y can be the Y and Q are interlinked. They are having the proportionality relation, remember. So you can replace Y with Q and name it as a conservative form. Okay, whenever you use the discharge, that means the volume of flow of flood you are explaining and calculating at the downstream side Hence, it is a conservation form of the momentum and conservation of the form of continuity equation. This is the one shape I would like to bring to your notice. That's it. Therefore, I brought this equation to my slide. So as I already told you that 1 upon S naught del O by del X is play a key role. That means water surface gradient. That means del Y by del X, the flow depth variation with respect to bed slope. Slope may be high, slope may be low. That I will explain more clearly. This term is very small, that causing some instability in the St. Valence equations. They have to be taken care while using these methods to compute the flood peaks in the downstream side. Now, the other forms of these bulk waves, these are the derived equations of the St. Valence equation, and we name them as simplified method because the original equation is brought into some other form using some other kind of mathematical functions and mathematical approaches. So that gives you certain forms. That forms are only be used to estimate the floods. Therefore, we call them as simplified methods. That means you might be using some binomial series to change the original form to some other form, or you might be using some other Taylor series to convert into some other finite difference scheme. So therefore, you are simplifying a original equation to some other form. So that is a derived form. So that derived form will have a shape. So that shape is being used in the model to develop the algorithm and to estimate the flood peaks. So these are the derived quantities or simplified quantities. Hence, those methods are simplified methods. So simplified diffusion waves will have the celerity component as a coefficient for the particular wave, and also diffusivity coefficient in this particular term. Whereas in a kinematic wave, as I already told you that the diffusion wave ACD equation, I already told you, approximate convective diffusion equation, is a transition phase of a kinematic wave. So as I already told you that, so this diffusion term, diffusivity term or coefficient can be ignored due to del Y by del X is tending to zero. That is one case study which we have seen. In that particular scenario, the higher order terms can be ignored to zero. Under such situation, diffusion wave can be converted into kinematic wave. So this is the transmission phase of a mathematical function. Similarly, if you see the continuity equation here, del Q by del T and del Q by del X is equal to 0, which is the kinematic wave. But here in a diffusion wave, still the coefficient of rho, diffusivity coefficient rho is there in calculation of diffusion wave force. But if you feel del Y by del X is having some considerable magnitude, yes, all the time del Y by del X may not be tending to 0, but it may be taken with some constant variations for a given length. It may be standstill water to a particular reach length. So under such situation, it cannot be equated to 0, unlike this case number 1. So in that such situations also, higher order terms can be ignored as the solutions for them is a little complex in nature. Hence, they can be ignored and convert or transform this diffusion wave to a kinematic wave situations. Okay, so with this particular scenario, so the ACD equation in conclusion I wrote here. So it means that 1 upon S naught del O by del X is the magnitude is playing a key role. That means the flow surface profile is playing a key role in defining the flood waves. So this theory is proposed by my professor, my guide, along with his own research scholar, and initially proposed by him with his own teacher, Professor Rangarazu. He wrote many books on open channel flow and a vice chancellor of University of Roorkee, then University of Roorkee. Now it is IIT Roorkee. So with this brief, I cannot say brief. It is a wide, lengthy discussion. So the categorically, we can now define the various types of floods, so various types of methods into flood routing methods into three groups, major three groups. One is using the NN model, black box models. My student, Mr. Reddy, who is the presently coordinator, has done some work under me using his empirical regression black box model. Of course, his results I'll be going to explain to you in my results chapter. So this is one method. Under my guidance, Mr. Reddy has done some work. Of course, he has not done ANN, but he has used some genetic algorithm approach to estimate the flood, which I can call them as black box model. So you are giving one input and getting some output. By prima facie trade-off you are developing by giving some weighing factor inside to match the computed values with the observed value and getting the answer by minimizing the errors in the model. So finally, you are getting some answer and saying that this is the computed values, then it and calibrated value, and this can be used for validation also. That's what the people are doing, widely using the NN model, algorithm based model. That is what it is. The other type of the routing method is hydrologic model. Hydrologic models, again, we can say, inflow and outflow relation. They use the time as the constraint for lumped models. Lumped models mostly called as the hydrologic models. Time invariant models are nothing but the hydrological model. So they can be, subdivided into linear storage model and non-linear storage models. Remember, therein we use the classical Muskingum method. So many BTech, MTech people might have studied the Muskingum method. So that comes under this hydrological model. Remember, we can do that in a linear mode and linear storage model and a non-linear storage model. And even moment match method also can be used by using some kind of time distribution and some kind of introducing some non-linearity in that particular model. So hydrological models in general, we call them as the time invariant here. Models, they usually use the continuity equation, remember. That means the change in storage with reference to time is calculated taking the difference between the input and the output. That's why hydrological models usually uses only the continuity principle, remember. So now when you go to the hydraulic models, we have categorically defined it in many ways that one is the dynamic wave, another is the kinematic wave type. So there also we have categorically told many, the methods in simplified mode and simplified modes where the Centralance equations are directly used and Centralance equations are indirectly used, remember. So in the directly used methods, we will take the continuity equation and the momentum equation and use them in the linear form and quasi-linear form. It means that apparently it is a linear, but it is not linear. That is called quasi-linear. It means that it is a non-linear phenomena, but not really non-linear, remember. So when you take a linear equation in one-dimensional flow and derive it to a certain form, so we can and maintain the non-linear flood behavior in a linear mode, so we can say it is a quasi-linear. So in that particular scenario, so we have developed the variable parameter methods in a quasi-linear approach. So finally, we have developed the VPMM method. So by deriving the quasi-linear derivatives from the using the directly the Saint Vanity equation. So apart from that, indirect methods also there. So that is Kalinin-Veliko method, or we are using a particular storage equation with a kind of nonlinear approach, a power term, using some parameters in the nonlinear mode, and we are optimizing that particular each and every parameter, computing the discharges at the downstream side indirectly. So that is also a hydraulic routing methods using the indirect approaches. So with these major classifications, whatever is seen here, you will come back class. Whatever method you see in the world now, so anywhere it falls in this particular block diagram. So So again, when you go into more details of the models, in particular VPMM, etc. So I wanted to again remind you that the water surface slope that is defined along the reach flow depth variation with reference to the bed slope is having a functional relation always with the bed slope S naught and the surface characteristics, that means roughness, and the initial flow depth that is available at the same time, initial discharge that is available at that particular time point, and also the time to peak of the flight and the discharge peak QP, that is the peak discharge. So that means the flood wave characteristics are fully depending on the physical characteristics of the river. That is very important. Any model that is developed based on these physical characteristics, we call them as physical models. Whenever you use ANN and black box models, you don't talk about all these parameters. You don't bother about what is the surface characteristic of a river at that particular section, whether roughness is high, roughness is low, you don't know. And the bed slope, how much, whether it's high slope or low slope, you don't know. What is the initial base flow at that particular river location or basin, you too don't know. And peak discharges, peak flow, how much it is, you don't know. And its symmetry of the flood, whether it is symmetric flood or asymmetric flood, is it gamma distribution type, yeah, beta distribution type, the shape of the or skewness of the flood, whether it is skewed towards right, towards left, or symmetric like normal distribution, that also the characteristics of the flood you do not know in the black box model, but still they are very popular as because the weighing component is governing at different layers to match the computed value mostly with the observed values, recorded values. And there you are trying to minimize the error using many algorithms like the Kalman filter techniques, reducing the error, or AR2 auto-regressive models, etc., or extended Kalman filters. There you are using to reduce the error in the model. So therefore, they are also popular, but they are non-physical models, remember. But when you compare the results between the non-physical model and the heuristic models like the black box models, obviously you will see the difference because flood is a natural phenomena. It's governed by the local situations, the local acceleration, convective acceleration, and bed slopes, surface characteristics, etc., and river, bends, vagara, etc. So obviously, I guess not only me, many researchers guess physical models will give better results compared to the non-physical models or black box models that I have already proved. Those results I'll be showing you in a short time. With this, let us now go to details of the basic concepts of the flood routing. First of all, just at an instant of time, you observe a flood wave as an observer standing on the bank of a river. You just observe what is the V1 at that particular section at an instant time t. Say here I said it is t naught. And after certain time duration, say 5 minutes or 10 minutes, like the delta t, maybe 30 minutes, etc. If the wave front, if you observe at a particular location, you will see three velocities at that particular channel location. That means you are imagining a flood wave traversing along a straight reach of a stream. Remember, uniformly with uniform flow conditions prevailing at that particular instant of time. So you will see at upstream side V1 flow velocities and downstream side V2 velocities. There is a change of velocities variation with respect to the locations or flow area variations and the cross-sectional variations. The velocities get changed. Remember, so in that process between this V1 and V2, you will see a wave celerity. That wave front gains certain wave celerity. That means that wave front velocity, that is the wave front velocity, will be governing the flow or the flood wave front. That type of the flood instantly, if you see, you cannot see any attenuation in it. The instantaneous picture is shown here at a particular location. That type of the flood wave movement or the wave, wave front, we call it a monoclinical rising wave front. Remember. So this picture I have picked up from one of other researchers, very popular researcher, contemporary of Professor Paramal, that is P.P. Mazumdar from IIT Bangalore. So this picture I picked up from his system. So this monoclinical rising wave is considered to be a uniformly progressive translating flood wave. Remember, it is a non-uniform flood wave. It is not a non-uniform flood wave and not unsteady flood. At an instant of time, you will see uniform behavior of the flood wave, but with a local velocities that is named as the wave celerity, wave front wave velocities, consisting of the upstream velocities and the downstream velocities at an instant of time t. So here, if you see in the flood routing, you can see it is unsteady flood flow with attenuations here. Okay, because the area is changing. Obviously, the flood characteristics will vary. The flood weak comes down. It has to go down because roughness is varying. So outflow, that means the flood discharge wherever it is estimated the downstream side, so will show a certain difference here. It cannot be a monoclinical type of rising. It is a kind of attenuation type of rising the flood wave, attenuation type of the flood wave that you can see due to unsteady characteristics that comes into picture because of the non-uniform flow characteristics or gradually varying flow characteristics. So that you are trying to characterize, calculate it using some methods. Apart from this, as I said, hydrology earlier, this is the channel methods, flood routing in channel. Now I can say flood routing in reservoir using only the continuity equations. As I already told you that they are all reservoir routing methods. So you have to construct one dam. There you will ignore the velocities because water is stored at one place as you have stopped the flow. So velocity impact on the river will not be there. It is gets nullified. Almost water gets kept as horizontal positions. So only you will see the flow depth variation with respect to area variation, storage variations, Y variations, etc. But the velocity impact is nil. That's why the storage is calculated as a proportional to the function of the volume variation only. Whereas in the channel routing, you will see the storage variation is due to the input and the output difference in the channel. That is the main difference. There you will be using the momentum equation. Okay, that there you will be using the momentum equation for calculation in the channel routing, whereas in the reservoir routing, you will be using the mostly in the continuity equation. Application of this flood routing is are here: peak flow estimation, peak forecasting, flood forecasting you can do, flood protection you can do, flood warning you can develop after calculation of the forecasted values, and you can develop some design water conveyance systems. Okay, and you can show some protective measures also, and you can develop hydro system operations properly, and you can say water dynamics engaged at the river stations. Okay. Now, this I have already told you. Whenever you use the hydraulic methods, as I said, it is space and time variant. When you lump method, it is only time alone variant. Remember, okay? This I have already told you. Yeah, here the equations. Each term I wrote here. It is suggested by Nerk in 1975. Categorically, he explained Sn del y by del x, v by g del v by del x, 1 by g del v by del t. He explained more clearly each term and its significance. Okay, so how that energy slope, that friction slope, is being calculated using this equation, physical equation is known to us. Yes. Now, when you go to the storage routing, that is reservoir routing. As I already told you, that storage is a function of the charge. So that means Q is having a function with the elevation, that is H, and storage indirectly a function of elevation. So those things you are calculating at the downstream side, giving the information at the upstream side that is inflow into the reservoir. So you are trying to calculate the outputs as a function of time, and consequently the storage as a function of time, the volume of the rate into the from the reservoir is also a function of time, and the flow depth variation is also a function of time. These are the things you are computing, taking the reservoir as the system and input as an input hydrograph sending to the reservoir. So for that, you are using the continuity equation, calculating the input minus output difference as the storage in a timely for a given time interval, delta t. If you use that delta t at two time levels, so the continuity equation will be referred like this: average of the inflows considered in that particular time interval, I1 plus I2 by 2, and similarly discharge Q1 plus Q2 by 2, the time average will yield the storage difference in that particular reservoir. So this is the hydrologic storage route. Go to the channel route. So again, I defined already, but the equations I'm now introducing here. So the channel routing will have the two phases in it. One is the prism storage, the other is the wedge storage. So the prism storage, that means the bottom layers of the channel here. So that is always having the uniform flow conditions, remember, and the flow is also steady uniform flow situations you can assume during the flood flow also, unsteady flow situations also. The unsteadiness, and you will see in the wedge form, but in the prism storage, since the depth is remaining same in the prism storage, that means the storage of the water in the river reach, you are making into two parts. So prism storage is having again proportional to the KQs, whereas the top layers of the flood, you will see the wedge shapes. Reason is that there is some difference of input and outflow. Sometimes inflow may be more than the outflows. Sometimes inflow may be less than the inflow. That means you will see the shape change, wedge shape change in the channel during the flow process while computing the discharge at the downstream side of the river reach. So that will create different concepts like a rating car in the river reaches, maybe normal during the steady flow situation, maybe a loop rating car in an unsteady flow situations. So during normal flow situations, you will see only one stage with reference to one discharge, wherein the rising stage situations, this rising and falling, that means the dynamic wave flood situations, non-uniform flow situations, you will see at one stage you will see two discharges here, two falling and two rising. So this is the physical changes that you come across in the channel routing process, wherein based on this logic, McCarthy, McCarthy, a river engineer, developed a storage equation that is adding the prism storage KQ plus the wedge storage K multiplied with I minus Q multiplied with certain factor, that is some theta weighting factor. He introduced it in storage calculation apart from the continuity equation. That's why I said this channel routing is of hydrological routing model, a classical hydrological model he developed using only continuity equation. Whereas we have revised these equations using the continuity equation and the momentum equation derived VPMM at the later phase, you will see that. Now, use of that particular channel routing, usually you take, as I already told you, that K is the travel time, variable travel time from peak to peak distance is the travel time or lag time, and the attenuation is defined with reference to the weighing factor theta. So this theta and K can be named as some constants because travel time can be fixed in a given particular reach, whereas inflow and outflow are the variables, so therefore storage also variable. So using that phenomena, so you can develop two varieties of problems here. One is the direct problem and the other is the indirect problem. So that indirect problem, we can say, is the inverse problem. That means you are using the input at the upstream side and computing the outstream outputs at downstream side, but estimating the parameters K and theta. That is the kind of inverse. That means you know the information at the downstream side and upstream side, and calculating the system parameters k and theta to balance particular storage equation. Yes, that is one approach. We call it as the inverse approach or indirect problem approach. And the direct approach is you don't know the output you are calculating. We say it is a forecasting mode of approach. So you know the travel time because it is already known to us because river is having many years. So travel times may be known to us. And theta is the weighing factor. You are assuming certain value from 0 to zero point 0.5. Okay, so usually for natural channels, we assume this theta is 0.25 to zero point 0.3. So based on this information, we will be, we will be calculating the outflow discharge at the downstream side. This is a kind of parameter estimation. Under this name, we do this. Next. Another classical method is already told you. This is what the Messingham method was when he developed hydrological method. The same thing. Here I am trying to explain all these things with reference to the theta variations. So you see 0 to theta and ranging between 2.5. Sometimes theta weighing factor is equal to 0. That is applicable only for the reservoir routing. Whoever do this channel routing, they don't assume theta as 0, remember. If it is the reservoir routing approach where the storage is proportional to K times Q, then you can take theta is 0. But for channel routing, theta cannot be 0. It may range from greater than 0 to 0.5. For full wedge, fully established wedges, it go up to 0.5. That is possible. When theta is going to 0.5, it is almost kinematic. If it is 0.3, 0.2, 5 something, it is a natural gradually varied flat wave or dynamic wave flat. Remember, in natural Deccan Plateau rivers, we see theta ranges between 0.3 to less than 0.3 or 0.35 maximum. But in glacier rivers, you see kinematic wave situations like Kedarnath flood event, the theta is almost touching 0.5, remember. So this is still McCarthy's method. So once you take the storage equations of the prism and the wedge storages at time level 1 and time level 2 and put it in the continuity equation and solve it, you will get a routing equation. You can calculate the discharge at a next time level in the form of forecasting mode. So one can easily calculate the discharge at the next time level, giving the information at the previous time level and the next time level, the input as an and the outflow at that previous time level as an inputs here, and calculate the next time level output here using some coefficients derived when you have substituted the storage one at time level 1 and storage time level 2 in the continuity equation. The coefficients C1, C2, C3 will be derived in terms of K and theta, and their sum should be equal to 1. And for better results, the travel time always keep more than the interval time, the routing time interval delta t, and it must be again the routing time interval must be greater than 2 times K times of the theta. Here theta actually. I written wrongly x. It is not x, it is theta. So these are the conditions that are required to use this kind of method. Okay, so I showed you some kind of drawbacks which you cannot see in the literature also. You see sometimes you see the theta is negative here. Outflow is occurring inside the inflow. This model having certain drawbacks. This was invented and explained by Professor Perumal in one of his papers. So he explained this point. This logic is sometimes theta is 0. Earlier I spoke theta is 0. So theta is 0, so I said it is the storage routing you can use. But sometimes theta is negative also. So that is causing due to insufficient reach length that is considered for insufficient reach length considered or not maintained proper reach length to compute the discharge at the downstream side. In that situation, theta goes negative. Otherwise, if it's sufficient theta is established there, so your outflow will be little crossing, intersecting the peak value of the outflow is intersecting the recession side of the inflow hydrograph at a little away distance. Remember, it is much on this similar. Yeah, the same logic now people have used in SWAT model. Popularly, people are widely used soft model. So this model people are using nowadays, using the classical Muskingum method, but in the form of Muskingum-Kunch method. Muskingum-Kunch has revised this classical Muskingum method into linear method into nonlinear fashion, using the timely invariant method. Actually, classical method speaks only time invariant, only time delta t, whereas is fixed. But the parameters, whatever estimated in the classical method, are for that particular time. So they are not varying. So what Kanj proposed that he has computed all discharges values in the timely varying mode and suggested is Muskingum Kanj method. So that is being used here in the SWAT approach. They are also developed the routing equation with certain parameters in other mode, and unlike this Muskingum, but they calculated the travel time. K is the L by C multiplied by 1000, where L and C are respectively our channel, the channel length. L is the channel reach length, and the C is the celerity they are considering here by 5 by 3 times of VC, where VC is the velocity. Flow velocity is considered in that particular river reach to calculate their charges at downstream side. So they are also using as a component model in the SWAT to compute the discharges in a basin model. Basin model, remember, basin model. So their coefficients also like this here, and their formations will be shown in that particular software like this. But the main drawback in this here is it is a constant parameter masking. Though it is timely varying approach they are adopting, but they are taking the reference discharge, which includes the average discharge in the river reach. That means the inflow and the outflow, they are taking an average mode, and they are adding the base flow that is coming into the river and naming it as a reference discharge. So that reference discharge is being used and to compute the flow depth existing at that particular location in a Newton-Raphson approach. That means they will be using the discharge information to compute the flow information in the Newton-Raphson approach, and they will calculate flow depth and supply into the model, and finally they will be calculating it. So whenever whoever uses this SWAT model for the river basin analysis, they have to be very careful about these constraints that are existing in that particular component model being used as in the name of MRM, remember. Okay, Muskingum routing method. Of course, it is a Muskingum Kanji method. Yes. So considering all these drawbacks, myself and my professor, have again thought of expanding this kind of derivative, basic fundamental equations into some other form, and named it as VPMM method to compute the charges, and again named it as a directly derived, as I already told you, that it is a directly derived hydraulic method, remember. Hydraulic method or a flow routing method. So again, we are using the French-Valence equations as the base models, and with certain approximations in a river reach. So section 1 is upstream reach, section 2 is the downstream reach. So I'm considering a river reach to a distance of del x, maybe a 5 kilometer, 1 kilometer, 3 kilometer, 10 kilometer, 20 kilometers, like that. I told you already, river bends have to manage the issues. So del x have to be selected based on the natural existing topographical conditions. Remember, of course, I will talk more on this deluxe approximations and the delta approximations also a little later phase. So reach is one, node one is upstream, reach two is node two, that's downstream side. If you take the middle of the reach is M, the middle of the reach is deluxe by 2. Now we have introduced another cross-section location, node level at section 3, that is in between the middle reach and the downstream reach, that we have named it as a normal section. It means a river in a dynamic in the process. As I told you, in the prism storage, you have already seen the characteristics. Okay, only the top layers have the prismatic section, prismatic, the wedge-shaped structure. Similarly, here also in the process of the flow movement, flood flow movement, you will see a steady flow situations in the river reaches. So that occurs at a characteristic length L, that I named it as the ratio of Q3, that is discharge available at that location, divided by 2 times S naught BC. Okay, so these are the components which govern this characteristic length. This is forming at a particular location that will cause a one-to-one relation between the upstream information to the downstream information. So when you want to calculate the Y3, okay, or the discharges at that particular discharge node, you have to use the upstream information. If you want to calculate the Q3, use the upstream flow depth information per calculation of the discharge. So that is what the requirement here. That's why I said Q3 calculations are having the functional relation of the flow depth exactly at the upstream locations. That is very near to that particular location. And the discharge that is calculated in the middle is having the flow depth information at that particular reach and also at the upstream information, that is YU. So with this particular logic, so one-to-one relations we are adopting and calculating the discharges at the middle, at the third section, assumed it as the normal discharges, considered under the unsteady flow situations. Okay, so with these particular assumptions, so we have calculated the downstream discharges using a particular grid approach. That approach here is the finite difference schemes we are approaching, making the section 1, section 2, and section 3, and middle reach here. So reach length is taken this side, and delta t is the time interval, the routing time interval, beginning at the j time level, and the ending time is the computed time is j+1. So to reach this j+1 time, we will be first calculating the information at the middle of the time interval, and that we are supplying to the next time level. That means central difference scheme approach we have developed to compute the outflows at the downstream side, giving the information at the upstream side, and in between we are computing the information that are required at the first section and also middle section. So that has developed that we have used the Saint-Venant situations converted into substituted in the binomial series that entities led us to develop a routing equation at the j+1 time, that means the next time level, taking the information at the jth time level along these flow direction and the time interval time scales. So these are the coefficients of the inputs. This is second coefficient. This is the third coefficient. So all this information, which is resembling the equation of McCarthy-Muskingum method, they are already discussed as the classical Muskingum method. Remember that. So in which we are calculating the parameter constant k of ratio between the reach length divided by the velocities, the normal velocities that are calculated using the information at the middle section of the reach at a particular time level. So that is the parameter we are calculating. Similarly, the other parameter also, that is theta, we are again calculating using this the values of the middle, the normal discharge calculated using the information of the middle and the bed width available, the channel cross-section width that is available at that location, and the wave celerity at the middle section, and the middle section wave celerity and the reach length, and considering the channel bed slope also. So all these will allow us to finally, write the equations like this in this way, and this equation is kept in the algorithm and calculated. If you want to calculate the normal discharges, so use this equation and calculate that. Okay. Yeah. This is one my summary of the final equations, which we have used in simulation mode, not in the forecasting mode. Forecasting mode is another concept. If time permits, I'll go. Otherwise, I can skip that. So, Muskingum routing equation, whatever the equation that is developed, which is resembling. So, in the form of discharge as I wrote, here the discharge that we are computing at the downstream side at J plus 1 next time level for a given time interval with the coefficients, which I have already mentioned here, which includes the time interval as well as the k values and the discharge at upstream side and the input. That means the input. This is input at upstream side and this is input at the upstream side at the time level, previous time level and the present time level. Say current time level. I am calculating the current time level discharge here, and I am using the discharge at the previous time level information, similar to the McCarthy method. That's why this variable parameter, that means K and theta are varying, hence its parameters are varying timely. So therefore, we have respected the Muskingum, though it is derived by us, but we respected the works of McCarthy, who proposed this original model, beautiful model, and given to the world. He worked this concept on Muskingum, river. Muskingum is a river; it's not a person. Remember, it is a tributary of Ohio River. Okay, so he named that as the Muskingum River equation. So we have respected him and named after him as VPMM, that is the variable parameter McCarthy Muskingum method. So that we have used and calculated. These are some other forms of the k values and theta values, which includes the flood, the fraud number. If you want to calculate, and if you want to calculate the celerity, these are the forms of simplified method. Originally started from the continuity equation, and the momentum equation, Segran's equations. So these are the forms of it. So any model that is developed, one has to verify it with certain evaluation algorithms, evaluation measures. Okay, we have calculated the discharge errors, time peak errors, and mass conservation checks, and the efficiency of the model, and the corresponding the flow depth variations, time peak variation, and the corresponding flow efficiency of the depth calculations. So we have calculated all these evaluations, checked the model performance using all these correct evaluation methods. Okay. After that, we have wanted to compare this model with the already existing popular model, that is MCT, Muskingum Thodini method. Actually, Muskingum Kanji method, whatever I told, now again revised by Thodini. And of course, that Muskingum Kanji Thodini method is also one of the popular methods developed in 2007, but it is originally brought from the Price, whom I worked along with my Professor Permal. That method is now, having a little basis from the Price original works and developed certain assumptions. He is also using the reference discharge concept with the constant parameters and with certain, complete some correction measures he applied to calculate the discharges at the downstream side. So these are the corrective measures he applied with correction, and without correction he worked out and developed one routing equation. His derivation, whoever wants to ask, I can support them, but all these derivations I can discuss at later phase. I'm just elaborating what others did, what we did it. Okay, so some corrective measures he explained and developed some algorithm, okay, and calculated the coefficients like us, but with correction and without correction. That is the D star value and C star value. Correction factors he introduced to get the correct answers, but it's a kind of quite cumbersome approach he developed. But okay, and computed the results. Okay, that is what. At the same time, his model cannot calculate the discharge and the stage at the same location. He will compute the discharge at the downstream side and the depth at the upstream. That is the drawback of this method. Where similarly, even if you use the Mike 11, Mike 11 also has got the similar drawbacks. That I will explain to you later. But whereas in VPMM, we can calculate happily the discharge and the stage. That means the flow depth at the same location. That is the beauty of that VPMM method. Okay. Apart from these concepts, physical methods, now I will just touch upon what the coordinator, Mr. Reddy, did under my supervision. Of course, he has only picked up the genetic algorithm only for his work. He has not touched the other block work models because of the time constraint he had with me during his MTech period. So we can compare these models with the non-physical models. That is artificial black box models. I can name them as artificial intelligence applications. So we have done some work in that also, and we have run the models of genetic algorithm, run the models of differential evolution techniques, particle swarm optimization techniques, harmony techniques, using the important routing equation in the form of nonlinear form. You see the storage equation, whichever is visible to you here, is having a power that is nothing but a nonlinear form of the storage equation. Nonlinear form of the storage equation. Here the K, theta is already we discussed. They are the parameters, and we have introduced the another parameter, that is m power term. If m is equal to 1, this becomes the linear equation. So using this storage equation, so you can develop some algorithms and apply the black box models of NN and etc. and compute the discharges at the downstream side. You don't give any river reach length. You don't give surface roughness. You need not give channel characteristics. Anything. You can only give the input and know the output. Already the recorded values are only do computation with weighting parameters, updating, mapping with the computed versus the output by minimizing the errors. That also another approach. This is what the algorithm is nonlinear. Okay, but we have already developed it and published also. And apart from all these things, just to explain you the method, we have the explicit method, implicit method, grid approach methods, and define different schemes. They use this invariance equation. One is 4-point method. In explicit method, it is the algebraic equations or linear mode they are used. Okay, remember that you will be calculating the dependent variables or extracted there in the explicitly at given time points, whereas in the implicit schemes, the dependent variables are computed or occurred in implicit mode in a nonlinear form. So they will be using space changes and time discretization approaches. We have to develop a grid in a spatial direction and a temporal direction, and you calculate the parameters. So these two are also available as a benchmark models. So Mike 11 using the 6-point scheme, implicit scheme, using the explicit scheme. Remember the user, please, for your information sake, I am mentioning these things. For our model, we have compared our model with the across, with this implicit scheme, that is Mike 11, and also St. Van's. That means the benchmark models are St. Van's model, algorithm based. You have to have an algorithm code for it. And Hackross is freely available. Michael 11 with DHI people, it is freely available sometimes, or on purchase mode, it is available. So people can use any model to compute the discharge rate at downstream sites. But Hackross and the Mike 11 needs the cross-sectional information at every node point. One should supply the cross-sectional information. What is the flow depth? What is the flow area? Everything you have to define and generate the cross-sectional file. That is very much essential to compute the values at the downstream side. Whereas in our method, that is required. That's not required at all. Remember, that's why it is a cheaper method. Yeah. Study investigations, I would like to just show. These are the methods which I would like to, I have shown you. Now I'll go to my some investigations. In nutshell, I will show you. I think the time is running. Now it's 11:52. I think I will rush to the. Am I audible to all? Coordinator?
Yes, sir. Yes, sir. Audible.
Yes, sir. So I'm just rushing to the results so that I will show the differences, results, how all models are differences I'll show you. And inventors, researchers, participants, please observe the variations in the results. With the 10 minutes time, kindly extend coordinator G, 10 minutes time for me. Okay, you have given me time up to 12 o'clock, but I will extend 10 more minutes because I want to show the results to all the parties. Okay, sir, please. So I also request my next successor to spare my little gap because I brought good information to all the participants. That's what I feel. Because these mathematical models people are afraid to touch upon. But these are very simple. One who knows small programming and small, differential equations solutions, they can simply attempt it. That's what my submission is. So with this particular submission, I'm now moving to my inventions that I have done and want to show you the difference between the physical model, non-physical models, and all models, whatever I just talked about here. Yeah, come here.
Yes.
Some applications, we have taken some hypothetical state studies. Channels we made as some rectangulars, trapezoidals with different varying sections. Slopes, side slopes we have varied, and breadth width we have varied, and rectangular, trapezoidal, triangular sections we have varied with this particular combination of the flood situations. Bed slopes we have varied. You see 002 is the high slope. I told you, I will be telling you what is high slope. 003, 1 in 1,000 use the high slope. 1 in 10,000 is the low slopes. Remember, so 1 in 10,000 is 0,001. Remember, that is low slopes. High slope is a steeper slope like a glacier river. Himalayan river will have the high slope 002, 003. Remember, okay. So 001 also a steeper slope. The mild slopes are 005, sorry, 0005, 0004 like that. So this is the bed slope variation. So you are creating the channel, slopes also varying, roughnesses from low to high, 0.06 high slope. You can go up to 0.09 also. Yes, we have gone. Okay. Here I'm showing up to 0.06. And 0.01 is a smooth surface. That is a glacier surface. In between 0.035 is a natural river surface roughness. And reach length, you have taken one reach length means upstream to downstream is only 1 kilometer, 2 kilometer distance, 4 kilometer, 6 kilometer, 8 kilometer, 12.5 kilometer, up to 33 kilometers that we have seen. Because the model, every model is having, it is the mathematical model, and that too, del x is a parameter, varying parameter. Okay, it has its limitations in approximations. You cannot take 100 kilometers at a stretch and run it like in Mike 11. People are running it 100 kilometer stretch, but they are taking del x as 1 kilometer, or del x is maximum 2 kilometer. That our friend will explain that. If you take only single reach without taking the sub reaches into consideration in that particular Hackross or the Mike 11 softwares, you will get a hazard results because the del x is a longer stretches will affect the computed values. affect the nonlinearity behavior. That's why, so del X and del T, even time also should not be a longer span. You have to limit them within the particular restrictions. But still, we have attempted with the smaller reaches and the longer reaches with the initial discharge base flows. Base flow means every river is having base flow, original initial flow. After that, river flow, flood comes into add. After raining, water comes into the main reach and its evolution takes place. But initially, river is having certain base flows, initial flows always there in the river. That is what I told. Initial flows gets affected due to construction of many upstream structure not allowing the flow into the downstream side. Therefore, river gets dried, flora fauna gets dried, environmental flows are dried, no flows are allowed. Then how to survive? The river gets dried, encroachments takes place, rivers gets diminished, or river gets this is what happening nowadays. People are not realizing this scenario situation. So to enlighten you, so I have taken different base flows and different discharges. Peak discharge here I have taken 900, and time to peak, the flood evolution time, I have taken 1 day, 24 hours, and the side slope 5 of the trapezoidal side, I have taken a total of 200 numerical, 250 numericals we worked out by giving the input hydrograph using this particular equation, whatever I showed in my slide, which is a Pearson type 3 equation that can be used. Your Reddy knows that how to use that. Use this equation. So that can be used to generate the flood on your own. You need not take the field data for the model development. You can create the channels. You can create the floods on your own. You can create every on your hypothetical situation and test the model and its efficiency. That's what these are the channel configurations we have developed with varying slopes, high to low, at varying roughnesses, at the different 25 channels, and compared the VPMM discharge model with that particular Muskingum Kanj Thodini model at for a deluxe of 100-kilometer stretch we worked out and seen that our model is showing a purely a mass conservative model. Muskingum McCarthy model. You see the red dots. It is the mass is totally conserving, whereas in MCT model mass is conserving exactly, but with slight modifications, slight errors in the mass conservation. But 0.5 error is not that much, difference. Remember, that model is also a mass conservation model. Remember, because when you take the volume as a consideration, so you don't bother about these small errors. Right? But when you take the depth as into consideration, you cannot ignore these errors. Remember. So this is what people should aware. So we have taken 1 upon S naught del V by del X. I told you, this is a flow profile referred with the parameters. So everywhere flow parameters we are referring, and we have calculated its model volume error, peak errors for the other rectangular channels. Here you can see, and these are all volume errors and peak errors also. You can see that peak errors, Q peak errors here in a trapezoidal model. Peak errors, the model whatever the Thodini proposed is more close to zero here. Errors, whereas our model is slightly deviating in the peak estimation. Remember, so this model is totally mass conservative in establishing the peak error slightly, inferior to this particular MCT. But the advantages of this VPCT and LCT, when you compare the overall these things, the model can compute the discharge and stage at the same place, whereas that model MCT cannot do that. Yeah, this speaks about the performance of the model overall, computed versus across. Here I have taken across as the benchmark mode. Okay, at later pages I have taken St. Valence, later pages also I have taken Mike 11 also. So these are the at 2 kilometer observation. At this is at again 2 kilometer for trapezoidal sections. You see, all of channels are falling on that horizontal line. That shows the beauty of the model. So whereas some computations or falling little away from this line, it means they have certain the considerations there, that maybe the slope is too much high, the roughness is too much high, sorry, slope is too much low, and the roughness is too much high, so that causing the error in the nonlinearity approximations, because the roughness is high and the slope also flat. So under such situations, behavior of the models cannot be explained morally. Physical models, that is because opposing the flow is opposed by the high roughness and the flat surface. So where is the flow? So in such situations, you can see such deviations. These are the another evolutions in trapezoidal sector between MCTs. Next. This I'm showing at a glance because time is going on. These are all various results that we analyzed at different. Now it is at 12.5 kilometers. At 12.5 kilometers means reach length is increased to a higher length. Remember, you see here also volume conservation wise we are superior over the other methods. Yeah, similar behavior at 12.5 kilometers. Just to at a glance, please see. If people want to interact with me, they can talk to me over phone or some other means. These are the discharges, the hydrographs that are computed, matching with the MCT and the observed values at 12.5 kilometer, at 2 kilometers, stretches with the slopes that are taken at the 0.025 and bed slope, and the roughness is the natural channel roughness 0.035. We have picked up. Okay. So this is the overall, rectangular and the MCT's observations. If you see these things, you can see the peak establishments here for different varieties of sub-reaches. 100, 200, 150, 25, 16, 1 sub-reach, 4 sub-reach, like that. We have different sub-reaches for a given 100-kilometer stretch. We made into separate sub-reaches and try to compute the peak values. You see with the variable parameter McCarthy is showing the peak estimations are accurately for sub-reach approaches, and for the MCT is little inferior. But if you see here, the dip of the initial dip of the flood hydrograph, so it is showing the negative side. Here for him it is a lower value. It means that the physical models usually will have to behave the initial stretch into consideration. For a longer stretches, the initial dip is high. For a smaller ditches, the initial dip is low. Since the VPMM is physically based, purely physically based model, so that is behaving like that. So for a longer reach, the nonlinearity is getting affected much. That's why it is showing here. Whereas here, the this is also showing that particular this thing, but it is controlled by the corrective measures that what he has adopted in it to get the correct answers. But he failed to produce the peaks of the flood at this place at a given time point. These are the differences. You can see some other information, the flood peaks of different. Here I have compared with the Saint Vanant, not the Hecras. Saint Vanant's equation, whatever we have, the derivation. So I compared with the varying. So this is a situation we created with the smooth roughness. You see the roughness is smooth, but slope is mild. And here the roughness is high, but the smooth slope is high, you see. And like that, I have created different environments and created. So roughness is high, but though it is high steep, but roughness high is opposing the flow, therefore causing the lot of attenuation here. This is what the observations one has to see. So physical behavior is seen here in the results. So this is one upon is not calculations for different these things to find out the applicability criteria of the method. We have worked out these things. Okay, for different channels, you can see the applicability criteria. We fix that one upon is not del y by del x is at 0.5 above that, and